So the principle I'm using here is that I have two different functions, f of x and g of x. I need both of them to be positive, and I'm going to say that f of x is squeezed between 0 and the value of g of x for the whole interval from a, including a, to infinity. I want to say something intelligent about the improper integral of f on that interval. And the intelligent thing to say here is that if the integral of g of x exists, then the integral of f also has to exist, and it will have to be less than or equal to the integral of g. So you might wonder, why is this true? I find the picture to be very convincing myself, but if you prefer to work things algebraically, then you can say that as I'm taking that limit for any value of t, the integral of f of x, the finite integral, has to be less than or equal to the integral of g of x, right? Integrals preserve this relationship for functions that bound one another. And then calculating a limit, if I'm thinking of this formula on the left is just telling me a number, this formula on the right is just telling me a number. The number on the left is smaller than or equal to the number on the right. I take the limit on the left, I take the limit on the right. The limit on the left has to be smaller or equal to the limit on the right. So for the integral that I pictured, e to the minus x squared, I can say that this improper integral, if it exists, will be less than this other improper integral, which I can actually calculate, right? So my definition of the improper integral says integrate from 1 up to t first, then take the limit as t goes to infinity once you know what this formula is spelling out. So in this case, my antiderivative is minus e to the minus x, and that means I'm taking the limit of e to the minus 1 minus e to the minus t. T goes to infinity, so this e to the minus t is going to 0, and my limit is going to be equal to e to the power minus 1. That means that this integral up here is going to exist, and it's going to be some number less than e to the minus 1.